Hello everyone, welcome to lecture number 1 of the third week. In this lecture, we will explore subsequences, its basic concepts, definition, and some of the examples. I will also explore complementary sequences, and then there is a theorem with the subsequences. We will prove that theorem analytically, and then we will see the application of that theorem. So let me start with the topics covered. We will cover definition and basic concepts of subsequences and the theorem analytically to prove that. What is subsequence? As its name suggests, subsequence means it is a part of sequence. But how you can visualize it? Let me give you formal definition of a subsequence. So subsequence is a collections, infinite collections of a sequence in which the numbers or the terms must retain their order. So the main and the most influence things in definition of subsequence is the order maintained by their terms. So a subsequence of a sequence is obtained by selecting certain elements from the original sequence while maintaining their order. As I told you that the order is the main influence, but not necessarily keeping every element. So mathematically, if xn is a sequence, then xn k will be a subsequence if nk is become a sequence, is a strictly increasing sequence of the natural numbers. So something like this: 1, 1 by 2, 1 by 3, 1 by 4, and so on. And if you are looking for only odd numbers, odd positions, so that will make another sequence, and this is called subsequence of this sequence. Now you can see that I have chosen the first term, the third term, the fifth term, the seventh term, ninth term, 11th term, and all these are strictly increasing, right? So that's what the definition is. Consider the first example: 1, 2, 3, 4, 5, 6. So this is a natural number n, right? It is a sequence. And now consider odd numbers. So 1, 3, 5, 7, 9, and so on. As you can see here, this become a subsequence. We have seen how it's become a subsequence because it retain their term, retain their orders. So their orders are maintained in the subsequences. Now consider 1 by n, as we have already done this, and look at for x 1 by 2k subsequence. So you are looking for 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, and so on. This is a sequence, and you are looking for even positions terms, the collections of the even positions. So even positions terms make this subsequences. So 1 by 2k is a subsequence of 1 by n. Similarly, consider a sequence minus 1 by power n. Now we can write this one: minus 1, the first term, the second term is 1, third term is minus 1, 1, minus 1, 1, and so on, right? Now take only the odd positions terms. So what will be the odd position terms? Minus 1, minus 1, minus 1, minus 1, and so on, right? So taking all the odd position make a subsequence. Similarly, you can take the even index terms, so even position terms. So 1, 1, 1, this will make a subsequence of that sequence. Similarly, we can have a sequence ABCD, right? ABCD and so on, and we can have a subsequence later at the odd position. So we have A, C, E, and G, and so on, right? Sequence, consider factorial n. So I can write this sequence as the first term is first 1, the second term is factorial 2, that means 4, and third term is 6, so 4, 6, and then the fifth term is 30, sixth term is 180, and seventh term is much bigger, like this, right? Now I will choose a subsequence which is divisible by 10 only. So in that subsequence 146 will not be available here, right? So what will be our subsequence? Our subsequence started with 30, 180, 180 cross 7 and so on, right? This will be the subsequences which is divisible by 10 only. Similarly, consider a sequence n square plus n plus 1, and I will choose it subsequence which are prime only. So let me explore for you. So write down this sequence. So put n equal to 1. If you put n equal to 1, it is 1 plus 1 plus 1 equal to 3. So the first term of this sequence is 3, right? Now look for the second term. So put n equal to 2. So 4 plus 2 plus 1 is equal to 7, right? This is the 4, this is 2, 6 plus 1 equal to 7. Now put 3. 9 plus 3, 12 plus 1 equal to 13. Now put 4. 16 plus 4, 20 plus 1 equal to 21, and so on. You can put 5, 6 and so on. Now the sequence only comprises of prime numbers. So 3 is the prime number, right? 7 is the prime number, 13 is the prime number. But what about the 21? 21 is not a prime number. So our subsequences becomes 3, 7, 13 and all those prime numbers which are in the sequence, all those prime numbers which are in that sequence. So this is a special type of a subsequence. Consider sequence all connected graphs. I believe that you understand the graph. So if you have this graph, something like this, and this is a connected graph, it's connected each terms, each corner, each of that edges are connected to each other. So this is a connected graph. And trees. So subsequence become trees. So I can took like this here, and then from this and from this. So this will be not this, but let me erase this first. Yeah. So this will be a trees, and this will become a subsequence. Similarly, consider a sequence minus 1 by power n. So what will be its terms? Its term is n equal to 1 will give you minus 1, n equal to 2 will give you 1 by 2, n equal to 3 is minus 1 by 3, 1 by 4, minus of 1 by 5 and so on. Now consider only positive terms only. So 1 by 2, 1 by 4, 1 by 6, 1 by 8 and so on. The sequence of all English words and the subsequences can be considered as the words with only vowels. So now we are at the words where we can understand the complementary subsequences. As its name suggests, complementary means something, the whole part and then the another part, right? So these two parts make the whole set of that one. So we will find this complementary sequences in the same way as we know the complement to each other, right? So let ANK and ANP are subsequences. So we have considered two subsequences ANK and ANP of a sequence AN. Then define S1. S1 is all those NK which are natural numbers. So this suffix NK and ANP. So this one will become S1 and this will become S2. So I consider all those natural number which are NK and all those natural number NP as a collections are S2, right? So S1 and S2 become a two non-empty sets because obviously natural number has something. So S1 union, the subsequences ANK and ANP are said to be complementary each other if S1 union S2 become natural numbers and both are disjoint. So S1 intersection S2 become phi or phi, right? Now remember this one, S1 union S2 may not be complete in N, but except finite subset of N, and S1 intersection S2 may be a finite subset of N. So what we are looking for, so we have a sequence an. So A1, A2, A3, A4, A5 and so on, right. So we have a sequence an. Now I consider a n k, and where nk is what? Nk is some specific natural numbers, collections of the natural numbers. So let's say a1, a4 and then a7, a7 and so on. These are the ank, these are the ank, a7 and so on, right. And what are the np? Np are again some of those. So a2, a5, then a8 and so on, right. So a and p is also the same thing, a2, a5, a8 and so on. Now look at nk and np. If both the union of these two subsets become the whole natural number, or except for a few, that means finite set, then these two ank and anp are said to be complementary each other. Examples of complementary subsequences, we have seen the example minus 1 by power n, in which odd position and even positions have the 1 1 1 and minus 1 respectively. So minus 1 is the odd index terms and 1 1 1 are the even index terms. And look at these sequences, right. So this index is let's say x2n plus 1. So this is 2n plus 1 index and this is 2n index, right. So these two makes the whole natural numbers. So 2n and plus of union of 2n plus 1 makes the whole natural numbers, and that's why both becomes the complementary sequence subsequences of the sequence xn is equal to minus 1 by power n. Similarly, look at this one, minus xn equal to 1 by n, and taking even index and odd index, both different type of things. So 1 by 2, 1 by 4 and so on, and this will become a complementary sequences of xn, right. Similarly, prime numbers, consider a sequence which consists of only prime numbers, and then complementary subsequence become primes of the form 4k plus 1 and 4k plus 3. So consider for such subsequences where each term is 4k plus 1 and 4k plus 3, then these two becomes the complementary subsequences of the sequence which consists of only prime numbers. Similarly, consider a sequence cos 1 by n. Then consider complementary sequences such as whose term n is even and whose term n is odd. So odd index and even index terms makes the whole complementary subsequences and makes the whole sequence cos 1 by n. So now we came at the positions where we have to define a very particular theorem. We call it subsequence limit theorem, in which we will see that if a sequence has a limit, if it limit exists, then every subsequence of that sequence must have the same limit and must converges to the same point, right. So we will prove it analytically, and if time permits, then we will go with some examples and some application of this theorem. So a theorem, if xn be a sequence in R, so real term sequence that converges to a limit L, capital L, then every subsequence xnk of the sequence xn also converges to the same limit capital L. That is our theorem, the statement of the theorem, and we are now to prove this one using the epsilon delta definition or epsilon n definition. So since it is given that xn is a converging sequence, converges to a limit point capital L. So by definition, given epsilon greater than 0, right, there exists a natural number capital N such that for all n is greater than capital N, modulus of xn minus L modulus is less than epsilon. So what we are looking for, this is true for every small n that is greater than, bigger than that fixed natural number n, right. And what we are looking, if you are doing this, so L minus epsilon is xn is less than L plus epsilon. So and L minus epsilon, L plus epsilon makes you what? It is makes you epsilon neighborhood of the limit point L. That means each term each term of the sequence xn where it belongs to L minus epsilon to L plus epsilon. That means epsilon neighborhood of L. That is our definition of convergence of a sequence. Now consider any subsequence x and k. I index is x and k. By definition of a subsequence, the indices n k are strictly increasing, meaning that for sufficiently large k, we have n k is greater than or equal to k. So let us go through the definition of this. So you can see here, n k, the indices x and k will become a subsequence. That means the indices n k is a strictly increasing sequence of natural numbers. That's what we have in our definitions. So now use that one. So nk, indices nk are strictly increasing, meaning that sufficiently for large k, we have nk is greater than or equal to k. For k belongs to a natural number. Any natural number k, nk must be greater than nk, right? Because it's a increasing one. For sufficiently large k is greater than an n, then nk, if k is greater than capital fixed number, this is the fixed one, right? This is the fixed one for epsilon. So a small nk, as a small nk is greater than k and this k is greater than natural number n, capital N, thus for all k is greater than capital N, we have x n k minus L is less than epsilon, right? So now x and k lying in the neighborhood of L minus epsilon to L plus epsilon, right? So and this is happened for every k is greater than the fixed number, natural number capital N. So that means since xn satisfies the definition for a convergence of sequence, we conclude that x and k converges to the limit point capital H as n tends to infinity. Hence every subsequence of convergence sequence also converges to the same limit point capital L, right? That is what the theorem says, and we have proved analytically. So remember this one and consider the sequence xn equal to minus 1 by power n divided by n. And so what will be the possible subsequences? The possible subsequences are 1 by 2, 1 by 4, 1 by 6, 1 by 8, and that means it leads to 0. It leads to 0 as n tends to infinity. And x2n plus 1, that is the odd index terms. So minus 1 by 3, minus 1 by 5, it also leads to 0. So where nk is a prime, so 1 by 2 minus 1 by 2, it's also going for a 0. So by the theorem itself. Consider the sequence xn equal to 1 minus 1 by n, and we have already learned that where it converges. So 1 by n is converging to 0, henceforth 1 minus of 1 by n also converges to where? 1. 1 minus 0 equal to 1, right? So it's also converges 1. So xn is a converging sequence, converges to a limit point 1. Now whatever the subsequences possible, and you can create that subsequences of that sequence, it also converges to 1 only. So x2n, so consider a subsequence x2n. So what will be the terms? 1 minus of 1 to n, so this is 1 by 2, 3 by 4, 5 by 6 and so on, right? So this is the odd index terms, and all these converges to where? All these converges to 1. Why? That a sequence converges to capital L, the every subsequence, not only a particular subsequence, but every subsequence of that sequence must converges to the same limit point capital L. So since xn converges to 1, this subsequence converges to 1. Also look at the sequence itself here, 1 minus of 1 to n plus 1. This is a sequence, and moreover it is a terms from this sequence, this xn. So that means x2n plus 1 become a subsequence of xn, and in that case since the theorem says that if a sequence converges to L, every subsequence converges to the same number L. So that's why without any check or without any calculations, we can say that x2n plus 1, which has the each term 1 minus of 1 2n plus 1, it must converges where? To 1, right? Similarly, xn itself is a subsequence, isn't it? So every sequence is by the definition itself is also a subsequence itself. So all subsequences are also converges to 1. That's how we can assume that subsequences are important by checking any sequence converges to the same limit point or not. So now consider a famous sequence 1 by n, and now consider all those possible subsequences. So firstly consider for even positions, then the odd positions, then some prime numbers, then 1 by n and so on. So look at this term. This is n square. This is also a typo. So here I am trying to write this xn is equal to not this, but this is 1 n squared. This is the typo here. So each term here is 1, 1 by 4, 1 by 9, 1 by 16, 1 by 25 and so on, right? So we have a sequence 1 by n, and we have the another sequence, we call it 1 by n square. Look at these two. So this is a sequence 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, 1 by 8, 1 by 9 and so on. This sequence is quite popular, and it is converging sequence, converges to a point 0. Now consider the another sequence 1 by 2, 1 by 4, 1 by 6, 1 by 8. So containing only the even positions terms. So x to n. Now where it converges? Without any mathematical calculations, by the theorem itself we can say that this sequence or subsequence converges to 0. Similarly, look at for the odd positions or odd position terms 1 by 3, 1 by 5, 1 by 7, 1 by 9, and all these converges where? To 0. Similarly, xnk where nk is a prime indexed term. So what will be the prime? This is 2, 3, 5, 7, 11, 13 and so on. So 1 by 3, 1 by 5, 1 by 7, 1 by 11, 1 by 13 and so on. It also converges to where? 0. And look at another one 1 by n square, which also converges to 0. So all subsequences also converges to the same limit point 0. So here I am going to end that lecture. If you have any doubt in any one, I may explore in the next 2 or 3 lectures, because all these 2-3 lectures consist of the subsequences and their related theorem, right? So thank you so much.